Hi all, welcome to second part of the video lecture on relational algebra. See, in the first part we discussed relational algebra, the basic operations select and project which are unary operations. Okay, now let's see more operations. So particularly the binary operation, the set theoretic operation, union, intersection, set difference. Okay, Cartesian product also. This is what we are going to see now. This set difference is otherwise called the minus operation or except operation, like that. Okay. So basically these are all binary operations, right? That means they are executed among two relations. Okay, and before applying that you have to ensure that they are union compatible. Okay, so even though it is written like a union compatibility, that doesn't says that this is a requirement only for the union operation. This is a requirement for union, intersection as well as set difference operation. Okay, so for the all the three operations, if you want to apply among relations, say in relational algebra, you have to ensure that the underlying relations are union compatible, right? Whether it is intersection or set difference or union. Okay, so what do you mean by union compatibility? So it is like you are going to apply these operations among two relations, right? Two tables, say R and S. Let the attributes of R be A1, A2, etc. An. Attributes of S be B1, B2, etc. Bn. So see this. The total number of attributes in both the relations should be same. So you can't write it like a Bm. Then it is wrong. Are said to be union compatible or type compatible if they have the same degree. So that is the first requirement. The total number of columns or attributes is what we call as a degree. So the degree should be same for both, and also their corresponding domain should be same, in the sense if you are taking domain of A1, it should be same as domain of B1. Domain only we are talking, like a set of all integer or whatever be the restrictions we have for A1, same should be there for B1 also. Similarly, domain of A2 should be same as domain of B2. Otherwise, it's meaningless. Okay, so this condition in general for any attribute AI and BI, domain of AI equal to domain of BI for 1 to n for all attribute. It's what we call as union compatibility. Okay, I may take an example so that this will be clear. So when you are doing this union operation and all, we need some kind of meaning, right? So randomly two different say relations and all you are taking union, that doesn't make sense. For example, this is my R. Suppose it is containing attributes like A1, A2, A3. So this is one relation I am having. Let's see the tuples. Now another one is something like S. So that is also having say 3 attribute, and because I want the degree to be same, and also the corresponding domains are same. In the sense, suppose here I am allowing say a set of all strings, it can be any string, say name of a person or something, AB, BB, randomly I am writing here. Now let's see, this A is here, and here I have a different person, say BC. Okay, something random names I am giving. So the domain only I want to be same, like a set of all characters or whatever it is. Okay, now let it be say some age information, and we are having some restriction like it is between this and this. Okay, 20 and 70, something like that. Say 25, 26 and 27. Yeah. Now I want this to be same, so it can happen, right? So for this one, let's take a different age. Okay, now A3 is another field, say their salary or something, say some dollar, 10,000. So here also I want it to be $10,000. Okay, because we are talking about union, and so let's see how what it will do when something is repeating. Okay. Now some other value you wrote here, 20,000, some 30,000, some say again this 10,000, like that. It can be anything, right? Now when you perform union of these two, what is the result? R union S. So it can be two valid relation, or it can be some relation which is generated out of some other Boolean algebraic expression. Whatever it is, the requirement is like the total degree of both should be same for doing this union operation. And once you do this union operation, you will get a result, and the result is going to contain say 3 columns. Now how will you name these 3 columns? First of all, you typically what we will do is we will rename this attribute, like this b1 you can rename to a1, as domains are same. If you before applying the operation you can rename them, and in relational algebra we have a rename operator also. Anyway, that we are not going to highlight. It is something like this row for renaming. So typically what you can write, like like a1, a2, a3. This way I want to rename attributes of S. That is the meaning. The attributes of S are like a b1, b2, b3 respectively. They will be renamed like this, something like this. So this is typically how we are applying. Then R we will keep as it is, and then between these two we are applying the union operation. So here this rename will happen. If that is the case, this can be done in a number of ways. Anyway, it is like I am changing name of this attribute that of this, so that the result will contain these attributes, because I renamed like that. Okay, now there is a uniformity. Now it will do this so basically relation is a set of tuples, right? So elements are not supposed to repeat. Here also not repeating. Anyway, there is no key value, but still if you are getting duplicates, automatically the duplicates will be filtered out by the project operation and all that, right? So no such hope of duplicates, provided this R and S are valid relation. It may be result of some other relational algebraic expression, or it can be direct relation taken from the table. Whatever it is, this is a requirement, right, before applying this. Yeah, because it is a set theoretic operation. Within a set, elements are not going to repeat. But if R and S, you can see something is repeating, right? So basically here we have a 3 tuple T1, T2, T3. Here we have a 2 tuples T4 and T5. So the basic union operation, what it will do, it will, one set I have a T1, T2, T3 as a tuples, and the values, union, you are doing union operation with the T4 and T5, and what is the result? Result will contain T1, T2, T3, T4, T5. Now if you are looking, this T1 and T4 are same, right? So after performing the union operation, so just like so initially it will do like this, $25 $1,000. Then this AB $26 $2,000. Then this BB $27 $30,000. Whatever it is, just copy all this value. AA $25 $10,000. BC say $30 $10,000, whatever it is. Now you can see that here two tuples are found to be same, right? So this first one and the fourth one, so it will eliminate the duplicate. So this T4 will be eliminated automatically by the union operation, because whenever you apply any operation, whether it is select project or any set theoretic operation, the result should be a relation. So that is our basic requirement from relational algebra. In a relation, the tuples are not going to repeat. If that is the case, such duplicates will be automatically filtered out by the relational algebra. Okay, so you got it, right? So why this union compatibility is needed. In a similar way, now you can do this intersection. So when it comes to intersection, can you tell me the result? Like the same thing, like a T1, T2, T3. I am just calling them like that, but intersection in the sense this T4 and T5, T1, they are actually, when it takes intersection, the result is T1 alone, in the sense, because that is common. This T1 and T4 are actually same, right? So even though I am calling it as T4, basically it is AA $25 $1,000. Here also AA $25 $1,000. So that is the result. Now similarly, you can take something like a set difference. So it's better to call it as T1 itself, because it is same, right? So why you have to give a different name? Okay, yeah. Then T1, T2, T3 minus T1 and T5. So if that is the case, set difference will give you T2 and T3, right? So like that the remaining operations will also work. Accordingly we get this. So whatever it is, this union compatibility or type compatibility is something important for them. So then only you can apply any of these operations. That is, the degree should be same and the domain of corresponding attributes should be same. Now this is how you can formally define this union, intersection and minus operations between two union compatible relations. So that is a requirement. R and S are two union compatible or type compatible relation. Union means the result is represented like this. It's a relation that includes all tuples that are either in R or S, like what we seen, or both in, right? And the duplicates are tuples are eliminated by default. Okay, intersection, the result of this operation denoted by intersection is the relation that includes all tuples that are in both R and S. Similarly, set difference is a relation that includes all tuples that are in R but not in S, right? You know the basic definitions from the set theory, right? So we will adopt the convention that the resulting relation has the same attribute name as the first relation. Okay, so so by default we have that convention, so that you don't have to rename like this. Even though you are not renaming b1 b2 b3 to a1 a2 a3, it will assume the result will have same attribute as the first one, like a1 a2 a3. So even though you are not doing it, okay. Now in SQL we have this operation union intersect, and so the for union the keyword is union on itself. Intersection, intersect is a keyword, and set difference except is the keyword in SQL. Okay, keep that in mind. That corresponds to the set operation described here. So in the sense what we described here is something which is not allowing duplicates, right? Which is treating the input as well as the output as a set. So those things are purely implemented in SQL using this keywords union, intersect and except. But in SQL, as we already know, sometimes it will allow the result without any duplicate filtering also, right? Where the output will be some multi-set. So the input may have repeated in tuples as well as output also may have repeated tuples, right? If you want to preserve the duplicates, you can use this something called as union all. Everywhere you add this all, okay, so that will preserve the duplicates. So it will not do this any duplicate elimination. So such a flexibility is there in SQL, but when it comes to relational algebra, there is no such flexibility. It will always produce a result as a relation, in the sense duplicates will be automatically filtered out, okay. But we in SQL we have both options. Now commutativity, you know, these things you already know from set theory, like the union is commutative, intersection is also commutative, and these operators are associative also. The order doesn't matter, right? So if you are looking at the difference operator, it is not commutative, you know, right? And similarly intersection and all, if you want, you can express as using union and set difference like this. R union S will contain everything. From that R minus S and S minus R, once you remove, you will get R intersection S, right? Here you have an example query that uses this union operation. So the question is like retrieve the social security numbers of all employees who either work in department number 5 or directly supervise an employee who works in department 5. So either this particular employee is working in department number 5 or he is a supervisor to some employee from department number 5. Okay. So now what you can do, as it is either or, you got a hint like we are going to apply this union operation. So independently you have to find out social security number of all employees working in department number 5, and you know how to find out it, right? Social security number of all employees working in department number 5. So first you have to apply this selection, department number 5, tuples you take. From that you are interested on social security number alone, right? So you just take this. If you want, you can merge it also. Like what you are doing is, from the employee table you are selecting all the tuples with the department number is equal to 5. Now from this result you are projecting those with, I mean you are just projecting the social security number alone, okay. So or you can split and you can store the intermediate result somewhere, and you can do like this. So this is something more easy in the sense, right, you will not get any confusion, or if you want you can write like this directly also. Now you are taking, I mean if you are writing like that, you can reuse this result, okay. So that one benefit also we are having. Otherwise you have to write it again. Like what you are doing is, from the set of all employees with the department number 5, okay, so either this employee is working in department number 5 or he is a supervisor to any employee in department number 5, okay. So directly supervise an employee who works in department number 5. So we already taken all employees from department number 5 using these two steps. Now we are looking at the supervisors of employees in department number 5. So they also, we need them also in the result, right? So from this department number 5 employees, you just project the super SSN, I mean the supervisor SSN. So that will trace the employees who are working as supervisor to this particular employee. Fine. Yeah. Okay, now these two result you can perform this union, like result 1 is containing all employees working in department number 5. Result 2 contains all supervisors of employees working in department number 5. Okay, so there may be some common elements also. Whatever it is, we are going to do the union operation. By default, the common elements will be eliminated of these two. Okay, so when you are doing like that, the first we have this result 1 is containing SSN. Here this is containing super SSN. If you want, you can rename like this. So this is also one way of renaming, or you can just write it will assume SSN for the result, the first one. Okay, so that I hope you understand how to write something like this. Okay, clear. Now the next operation is Cartesian product. Cartesian product or cross product, and you know what it is, right? So let me take the same example if there is space. Okay. Can I use the same example and tell you how this Cartesian product is working, or you want a different example? So I think I don't know how to, otherwise everything I have to repeat. Okay, so let me just tell you, if you want to do this R cross S, so that is the next operation we are going to explain. R Cartesian product S. Now the result is a new relation, say Q, you can use any name, and that contains all attributes of R and S first of all. Okay, so it is like here A1, A2, A3, B1, B2, B3. Everything will be there in R cross S. A1, A2, A3, and B1, B2, and B3. And first of all, here we don't have a requirement like union compatibility. That is not needed. Okay, let me take a different example, because this example is basically having that union compatibility that is in mind. Okay, so we will take a different example and we will see. So basically, when you have a two relation, so it's a binary operation, right? And there is no requirement for this, like it do not have any union compatibility, so that is not needed. Okay, so R is containing some attributes from A1 to AN. It can be anything, any number, and BS is containing some BM number. So in the that itself says that the degree is not same. Okay, and the domain, nothing is to be same. Okay, union compatibility is not needed. And finally, the result is going to contain this n plus m number of attributes. I mean, all attributes of R is to be copied, then all attributes of S is to be copied. So that will be your result. And what is a Cartesian product? The basic from set theory, what it is, right? So what we can take is, I think I will take this example. So this is something interesting. So with that itself, I will take the example. Okay, I mean, with respect to this, retrieve the list of names of each female employee's dependent. So this is the question I am having. I want to know the name of female employees dependents. Okay, and so this is from the basic company database, where we have this employee table and a dependent table. From the employee table, look at all employees who are female. Okay, so you can just check the sex attribute, and you can see for those employee who are having the sex is equal to F, you filter them. Okay, horizontally partition it and filter them, and then you can look at the, so now when you are filtering it, you will get the entire thing, right? But we are not much so you just want to finally you can print the first name, last name of the employee who is a female, and the name of the dependent. So that is enough, right? You don't need the whole information like what is address of the employee, what is address of the dependent, what is salary of the employee. Everything is not needed. Our query is like you want to know, the user is interested to know name of dependents of female employee. That's all. So you can just display this is the name of the female employee, and these are all the dependents that person is having. So finally you are interested on that only. So you so when you have a selection query like this, here you will get the all tuples satisfying this criteria, and from that you are projecting just a first name, last name, and social security number. Why you are projecting social security number? Because using the social security number of the employee table, you will be referring the dependent table, right? Dependent table where this social security number is stored as a foreign key. I don't know whether you remember, and there we given a name like ESSN, like employee SSN. So this is something systematically coming actually. So if you are coming to this video directly, you may find it difficult to follow, because we already seen what is ER model and how this ER model can be mapped into relational model, and everywhere we are taking a single example, that is a company database, and this SSN, ESSN, everyone we saw during that mapping procedure. Okay, so basically SSN is a social security number, which is a key attribute of the employee table, and there is another table called a dependent table, where we have details of all dependents, and along with that we maintain the social security number of the employee who is the owner in the sense for this particular dependent, right? Now this comparison is basically happening to trace the dependence of a given employee. Okay, so now let me tell you. So like so these two steps are clear, right? So using these two steps, first I filtered all the female employee, then from that I taken first name, last name and social security number of the female employees. So far I didn't touch the dependent table. Okay, so let me just highlight this. So what I have taken is the first name, last name and social security number of the female employee. So this is one relation I am having. Okay, so they are giving a name for this, like employee names, something like that. So female employees. From that we are just interested at the name of the female employee. So it is given a temporary name, EMB names. Okay, so this is the first table I am having, employee names. Okay, whatever it is. Now you can assume different employee. For the time being, let's take some small examples. Say I have a female employee. Say this is a name. Something you write randomly. Okay, and now this is another one. Okay, social security number is say 101, and this person is having a social security number 102. Now there is another employee, social security number is like this. So suppose for the time being, in the current relational state, I am having only 3 female employee working in the organization, and that's an example I am taking. Now on other side, you know what I am having is the dependent table, the complete dependent table. Here this is the result of the query I applied. Okay, so when I applied that query, I taken the female employee, then from that I am projecting only relevant fields. Okay, now other side I have the complete dependent table, and I hope you remember this dependent table, where we have a field called dependent name, dependent address, age, say relationship to main employee. Yeah, like that many informations are here. Okay, you don't have to worry about all of them, or let me take for the time being. Okay, no need, because that is a complete table. All informations are there, let it be there. Okay, so the further details of the dependent will follow. And there is a field, and this field is what is interested, employee SSN in the sense, and you know this was acting as a foreign key in the original employee table with the SSN as a primary key. Okay, now this is not the original employee table, it is just a partial one that is resulted from the employee table. Okay, so actually this is going to point to the main employee table primary key as a foreign key. So anyway, I am removing that, you hope you remember. Okay, now this here you can see, even though it is a result, this is found to be unique in the sense, because original table SSN is a key, after doing the selection also SSN will still be a key, right? And here I remember, like employee the SSN and dependent name together is acting as a key. Together is acting as a key in the sense there may be many employee, or one employee can have more than one dependent. For example, this employee 101 itself may have as a dependent, say D1. 101 itself may have another dependent D2. Okay, so like that. So this field can repeat, right? So this employee, if you are looking at this ESSN alone, it is repeating actually. Similarly, what about a D name? It was a partial key, hope you remember. For a given employee, this field is not going to repeat. So when you take this one and this one together, it can repeat. I mean, it is not going to repeat. Why I am highlighting like that? If you are looking at employee number 103, he may also have a dependent with the name D1. Because that name as a whole, we are not, it's not a good thing, like you are compelling like the name should be unique for everyone. because two people may have the same name, same initial, everything, right? So that can happen. So what we are doing is like we are allowing name to repeat, no issue, d1 like that, but for a given employee for dependents we are not allowing names to repeat. So such a field is what we call as a partial key. Now you can see this partial key d name alone is repeating, this ESSN alone is repeating, but together it is not repeating, so together it is acting as a key. So those things we already discussed in that model mapping everywhere. Okay, so now this is let this be the scenario, so that suppose this employee 1 or 2 who is a female employee is not having any dependent. That can also maybe a bachelor or something. For the time being, that employee is not having any dependent. This can also happen. Okay, now what I am going to do is I am going to explain you the Cartesian product between these two. So first of all, there is no requirement like the both of them should contain same number of degrees. So here it is just a 3, here it can be anything. We are putting etc here, any number of attributes. So when you take the Cartesian product, what is happening is in the result, see in the result we have we will copy all attributes of the first relation, that is first name will be there, last name will be there, social security number will be there. So here you don't have to worry, only 3 attributes are there. Now when you are looking at the other one, employee SSN, which is a foreign key referring this SSN, right, is there. Then dependent name is there. Okay, and relationship of the dependent with the employee is there. Okay, let me write like that, and all other fields are there, so you should not disturb any of the fields. Okay, so something like this you will be getting. Now you know the normal Cartesian product, see how many tuples we are having here. This is tuple 1, this is tuple 2, this is tuple 3, this is say tuple 4, tuple 5 and tuple 6. Okay, see now how many entries will be there in the result. Say what is happening here is I have a set with the tuples t1, t2, t3, which I am doing Cartesian product with another set t4, t5, t6. And you know when you do this Cartesian product, you will get ordered pairs like t1 will be paired with t4. So now it is a new tuple, t1 and t4 together is a new tuple. Okay, so here what is my t1? T1 is containing values like AA, BC, 101. It is going to be paired with the t4, in the sense 101, dependent 1, etc. like that. Now the second entry will be the same, t1 will be paired with the t5 also. Okay, so that you will get it like AA, BC, 101. What is t5? 101, d2 and further details. Now the same t1 will be paired with the t6 also. So this is how you are taking the Cartesian product, right? That is this AA, BC, 101, this is 103, D1. Okay, whatever it is, it will go like this, right? Similarly, this then T2 will be paired with the T4. Okay, so when you are doing like that, what is your T2? A, B, C, C, 102. So it will be paired with the T1 means 101, D1 and other details. Then this T2 will be paired with the T5 also. So T2 is A, B. Hope you are getting right. Why I am writing is I want to explain something more from this point. So that's why I am writing it completely. Like here it is 101, say D2, etc. Now what is the third one? T2 will be paired with the T6. Okay. So this T2 AB, CC, 102 is going to be paired with the 103, D1 like that. Okay. Now this T2 is over, then T3 will be paired with the T4, T3 will be paired with the T5, T3 will be paired with the T6. So like that, how many are there? So what is the cardinality of this thing? So cardinality of this thing is going to be 3 into 3. There will be 9 ordered pairs. So that concept you know, right? So let me write the last one also. That is AC, BB, 103 is paired with the 101. I mean T4, okay, D1 and other things. Similarly, the same AC, BB, 103 is going to be paired with the 101, D2 for the things. Same AC, BB, 103 is paired with the 103, D1, etc. So totally 9 tuples you are going to get, okay, in the result. So this is the Cartesian product operation. Now this you may find like meaningless. Simply you are doing all pairing and the result you are getting something like this, right? Now how can you give a meaning to this concept? Okay, so first of all, here some extra points are there. These things, when you are doing like this between R and S, let the cardinality of R be some NR. The first relation is containing some NR number of tuples, and the second relation is containing some NS number of tuples. Then R cross S is going to contain NR into NS. In our example, there are 9 tuples. Okay, so you know these things, and now you can generalize it for N relations also. So what we are discussing here is just binary Cartesian product. Similarly, you can think of ternary, where you will get ordered triples, right? And n-ary Cartesian product also. So like that you can generalize. Now this is important. It is mostly useful when this Cartesian product is followed by a selection that matches the values of the attributes coming from the component relation. So when you done like this, so now we are at this step number 3. So what we done is, here we taken details of all female employees, and further we taken only first name, last name and social security number of the female employees. That is at one side we are having. Another side we have the entire dependent relation. We taken the cross product of these two. Okay, so that I explained with a small example like this, and this is the result I am getting. Now from this point, how we are proceeding? So what is the question? Retrieve a list of names of each female employee's dependent. For each female employee, so I have the list of female employee, fine. I want to know their dependent details. Okay, now can you tell me, so this is the first female employee I am having. Who is that? AA. Okay, so who is dependent of AA? Just look at AA. This female employee is having a social security number 101. Now you just look at the dependent table. You can see that D1 is a dependent of 101 and or this 101. SSN. Similarly, D2 is also a dependent of the same employee. But this one, even though I am giving the same name, this is for, this 103. So this is a different person, right? So you can, how can you ensure this? I know that this D1 is a dependent. For this AA, this is also a dependent, right? Now even though I am giving the same name D1, but now I mean a different employee here, okay? Okay, fine. So for example, relationship, when you are writing like this, say it can be father, mother, or it can be, so that can also repeat. We can't excuse for the time being, let it be something like that, mother or something. Okay, anyway, we don't want that much detail. Hope you get it right, because here why I written it as D1, chances are there for two employee to have same dependent name, right? So here, so you can correlate like this for the time being. Like for 101, I have a dependent name D1. This D1 I mean for 103 is dependent. So anyway, this 103 is dependent. I am not interested. This I am not interested. I am interested only these two entries. And similarly, if I am looking at employee AB, you can see that this is a social security number, and here there is no dependent for this person. Okay. So this Cartesian product is taking some 3 combinations, and they are all meaningless, right? I am not interested with that, because employee AB is not having any dependent. Now if you are looking at employee AC, you can see that the only dependent is this one. Okay, this third one, this T6. If you are looking at this one, this D1 is a dependent. So here also the other 2 combinations are meaningless according to me. Okay, so how you are filtering this is very important. So see this. So the matching criteria here is SSN and ESSN, right? So for these 2 tuples, these 2 things are same. So whenever there is a mismatch between SSN and ESSN, discards those tuples. I am not interested on any of these tuples, because ESSN and employee SSN, they are mismatched, right? Finally here again I am getting a match. So finally what I am interested is, I just want to know the female employee name and their dependent name, so that the final result will be something like the final result will print this, the first name, last name and dependent name of female employee. In the sense, it will print like AA, BC, D1, AA, BC, D2, AC, DB and D1. So like that, only these 3 tuples only I am interested. Fine. So what are all the things you want, that you can project finally, but in between this step is very important and is very crucial. So just by applying this Cartesian product alone is meaningless. Followed by Cartesian product, you have to give a selection condition like that, by which you will match the values of the attributes in a meaningful way. So here we are interested on, right, so the actual dependence of the given employee. So if you are looking at these entries, they are not giving information about the dependence. This is just pairing only. I don't want it, right? For example, 102 is getting paired with T4, T5, T6, but they are all not going to be dependent of this employee with 101. 102, he is not she is not having any dependent, right? So that is a scenario. So all these pairings are meaningless. After applying this selection criteria, I'm getting the meaningful information, where out of this 9 entries, I will be filtering out 6, and only 3 are final result, right? And from those 3 tuples, I am highlighting or projecting first name, last name, and the dependent name. So that will give me the final result. So this is very important. Cartesian product, even though it is defined as a relational algebraic operation by alone, it is meaningless. Always you have to apply a selection condition followed by the Cartesian product that will infer you meaningful information. Okay, so now we have a different concept called a Cartesian product followed by selection condition. We typically call it using a different operation called join, right? Now instead of using these 2 steps, what you can do is you can apply a single operation called join operation that will do this Cartesian product along with the selection conditions. So join operation typically we denote it like a let me just write here. So what you have to do is you have to write like this, say employee names, right? This is one table I am having, and other side I have a dependents. So in between, instead of applying Cartesian product, you have to apply something called as join. Typically for join operation, Cartesian product symbol, we will close this. So this symbol now means join, okay? And as a join condition, this selection condition will be mentioned like SSN is equal to ESSN. So if you write using a single step like this, so this is equivalent to these 2 steps. In the sense, I am doing that Cartesian product followed by selection operation that will give the final result. Okay, so this is my join operation. So this join is what we are going to discuss in the next video. So we will see join, the pure form and its variation, everything. Yeah, hope you get it right. So why it is defined as a new operation? Because this combination is something very important, and that is having a meaning, and it is repeating mostly, right? It's a very frequent operation. That is what I can tell you. So here you can see the Cartesian product creates tuples with the combined attributes of the 2 relations. Simply randomly they are making all possible combination. We can select the related tuples only from the 2 relation by specifying appropriate selection condition after the Cartesian product, as we did in the preceding example, because this sequence of Cartesian product followed by a select. Okay, so the sequence of Cartesian product followed by a select is quite commonly used to combine related tuples from 2 tables. A special operation called join is being was created to specify this sequence as a single operation. Okay, so yeah, that about it. We will explore join operation more in the next video. Thanks for watching.